Hello everyone, welcome to the lecture series on computer architecture and organization. This is our second lecture under Unit 5. In this lecture, we are going to see about what is hardware multithreading. So multithreading and chip multiprocessors. The most important measure of performance for a processor is the rate at which it executes the instruction. This can be given by MIPS rate is equal to F into IPC, where F is the processor clock frequency in megahertz and IPC is the instructions per cycle, is the average number of instructions that are executed by cycle. Accordingly, designers have pursued the goal of increased performance on two fronts. So that is increasing this clock frequency and this increasing the number of instructions that is executed, or more properly, the number of instructions that complete during a processor cycle. So as we have seen in earlier chapters, designers have increased this IPC by using an instruction pipeline and then by using multiple parallel instruction pipelines in a superscalar architecture. With pipeline and multiple pipeline designs, the principal problem is to maximize the utilization of each pipeline stage. So to improve this throughput, designers have created even more complex mechanisms, such as executing some instructions in a different order from the way they occur in the instruction stream and beginning execution of instructions that may never be needed. But this approach may be reaching a limit due to complexity and power consumption concerns. So, an alternative approach which allows for a high degree of instruction level parallelism without increasing the circuit complexity or power consumption, which is called this multi-threading. In essence, the instruction stream is divided into several smaller streams known as threads, such that the threads can be executed in parallel. The variety of specific multithreading designs realized in both commercial systems and experimental systems is vast. So in this section, we give a very brief survey of the major concepts. So these are all the definitions of the threads and switches. The concept of thread used in discussing this multi-threaded processes may or may not be the same as the concept of software threads in a multi-programmed operating system. It will be useful to define these terms briefly. One is the process. So the process is nothing but an instance of a program running on a computer. So a process embodies two key characteristics. One is the resource ownership and another one is scheduling or execution. So what is a resource ownership? A process includes a virtual address space to hold the process image. The process image is the collection of program, data, stack, and attributes that define the process. From time to time, a process may be allocated control or ownership of resources such as main memory, I/O channels, I/O devices, and files. So, this scheduling and execution. The execution of a process follows an execution path through one or more programs. This execution may be interleaved with that of other processes. Thus, a process has an execution state and a dispatching priority and is the entity that is scheduled and dispatched by the operating system. So this is the process switch, an operation that switches the processor from one process to another by saving all the process control data, registers, and other information for the first and replacing with the process information for the second. Thread, a dispatchable unit of work within a process. It includes a processor context, which the program counter and the stack pointer, and its own data area for a stack to enable the subroutine branching. A thread executes sequentially and is interruptible so that the processor can turn to another thread. So what is a thread switch? The act of switching this processor control from one thread to another within a same process. Typically, this type of switch is much less costly than a process switch. Thus, a thread is concerned with scheduling and execution, whereas a process is concerned with both scheduling execution and the resource ownership. The multiple threads within a process share the same resources. This is why a thread switch is much less time consuming than a process switch. Traditional operating systems such as earlier versions of Unix did not support threads. Most modern operating systems such as Linux, other versions of Unix, and Windows do support thread. A distinction is made between the user level threads, which are visible to the application program, and kernel level threads, which are visible only to the operating system. Both of these may be referred to as explicit threads defined in software. So all the commercial processors and most experimental ones use explicit multithreading. Concurrently execute instructions from different explicit threads, either by interleaving these instructions from different threads on shared pipelines or by parallel execution on parallel pipelines. So implicit multithreading is refers to the concurrent execution of multiple threads extracted from a single sequential program. These implicit threads may be defined either statically by this compiler or dynamically by this hardware. In the remainder of this section, we consider only this explicit multithreading. So broadly speaking, there are four principal approaches to explicit multithreading. One is the interleaved multithreading. So this is also known as fine-grained multithreading. The processor deals with two or more threads context at a time, switching from one thread to another at each clock cycle. If a thread is blocked because of this data dependencies or memory latencies, the thread is skipped and a ready thread is executed. And the next is block multithreading. So this is also called as coarse-grained multithreading. The instructions of a thread are executed successively until an event occurs that may cause delays such as a cache miss. This event induces a switch to another thread. This approach is effective on an in-order processor that would stall the pipeline for a delay event such as a cache miss. And the next is simultaneous multithreading, that is SMT. So here the instructions are simultaneously issued from these multiple threads to the execution units of a superscalar processor. This combines the wide superscalar instruction issue capability with the use of multiple thread context. And the next thing is chip multiprocessing. In this case, the entire processor is replicated on a single chip and each processor handles separate threads. The advantage of this approach is that the available logic area on a chip is used effectively without depending on ever increasing complexity in pipeline design. So this is about this approaches to executing these multiple threads. For the first two approaches, instructions from different threads are not executed simultaneously. Instead, the processor is able to rapidly switch from one thread to another using a set of registers and other context information. This results in a better utilization of the processor's execution resources and avoids a large penalty due to cache misses and other latency events. This SMT approach involves two simultaneous execution of instructions from different threads using replicated execution resources. Chip multiprocessing also enables the simultaneous execution of instructions from different threads. So this given figure that is based on that is UNG02, this illustrates some of the possible pipeline architectures that involve this multi-threading and contrast these with approaches that do not use this multi-threading. So each horizontal row that represents this potential issues slots or slots for a single execution cycle. That is, the width of each row corresponds to the maximum number of instructions that can be issued in a single clock cycle, and the vertical dimension represents the time sequence of clock cycles. An empty slot represents an unused execution slot in one pipeline, and no op is indicated by n. If you see this first three figure, the first three figure illustrates that shows the different approaches with a scalar, that is the single issue processor. So the first is the single threaded one. So this is a very simple pipeline found in traditional RISC and CISC machines with no multi-threading. And the second thing is interleaved multi-threaded scalar. This is the easiest multi-threading approach to implement. By switching from one thread to another at each clock cycle, the pipeline stages can be kept fully occupied or close to fully occupied. The hardware must be capable of switching from one thread context to another between these cycles. And this blocked multi-threaded scalar, in this case, a single thread is executed until a latency event occurs that would stop the pipeline, at which time the processor switches to another thread. So in the case of interleaved multi-threading, it is assumed that there are no control or data dependencies between the threads, which simplifies the pipeline design and therefore should allow a thread switch with no delay. However, depending on the specific design and implementation, block threading may require a clock cycle to perform a thread switch as illustrated in this figure. So this is true if a fetched instruction triggers the thread switch and must be discarded from the pipeline. Although this interleaved multi-threading appears to offer better processor utilization than this block multi-threading, it does so at the sacrifice of single thread performance. The multiple threads compete for cache resources, which raises the probability of a cache miss for a given thread. More opportunities for this parallel execution are available if the processor can issue this multiple instructions per cycle. For example, if you see the figure from D to I, that is up to here, it illustrates a number of variations among the processors that have hardware for issuing 4 instructions per cycle. So the given figure, that is the C figure, that shows a situation in which the time to perform a thread switch is 1 cycle, whereas in this figure, it shows the thread switching occurs in 0 cycles. So these are all the example system. The most recent models of the Pentium 4 use a multi-threading technique that the Intel literature refers to as hyper-threading. In essence, the Pentium 4 approach is to use SMT with support for 2 threads. Thus, the single-threaded processor is logically 2 processors. The IBM Power 5 chip, which is used in high-end power PC products, combines chip multiprocessing with SMT. The chip has 2 separate processors, each of which is a multi-threaded processor capable of supporting 2 threads concurrently using SMT. Interestingly, the designers simulated various alternatives and found that having two-way SMT processors on a single chip provided superior performance to a single 4-way SMT processor. The simulation showed that the additional multi-threading beyond the support for 2 threads might decrease the performance because of cache thrashing, as data from one thread displaces data needed by another thread. So that's all about this hardware multi-threading. Thank you.